everybody. In this podcast, I'll be talking about thermochemistry and energy transfer between systems and surroundings. Energy is the ability to do work, and in chemistry, the terms we often use are heat and temperature. So temperature is the way to measure the heat of a system, and heat really is the energy. And in chemistry, temperature change is associated with kinetic energy. And if you remember from the gases podcast, that the average kinetic energy of a gas sample is directly proportional to the absolute temperature. So temperature and kinetic energy have a direct connection, while potential energy has no connection with temperature. So during phase changes, if you've noticed that the temperature of a system does not change, that's because the energy given to the system during the phase change, like melting or boiling, this energy is used to overcome the intermolecular forces of attraction, which translates into potential energy, and kinetic energy is not impacted. Hence, during phase changes, the temperature of a system does not change. The units that we commonly use for energy are joules. However, joule is a small unit. Calorie is 4.184 joules. Sometimes we also use kilojoules, which is 4.184. Sometimes we also use kilojoules, and 1 kilojoule is 10 power 3 joules. And the conversion between calorie and kilocalorie is the same, 10 power 3 to 1. Then in terms of system and surroundings, in thermochem, everything is with regards to the system. If a system absorbs heat, we call it endothermic reaction. If a system releases heat, we call it exothermic reaction. So what's a system? A system is part of the universe where our focus is. System could be just the molecules. System could be molecules and the air around it. System could be molecule, this piston and the cylinder. So it depends on different situations. The definition of system can vary. Surrounding is everything around the system. And between system and surroundings, there is heat transfer. When a system absorbs heat, it is called an endothermic reaction, or delta H is positive. And when a system loses heat, it's called an exothermic reaction, and delta H is negative. The energy diagram for an endothermic reaction and an exothermic reaction. So if energy is on the y-axis and reaction progression is on the x-axis, then for an endothermic reaction, let's say this is the energy of reactants. Because the reactants absorb energy, the products will have a higher energy. While for an exothermic reaction, the products will have a lower energy than the reactants. And the difference between the energy of reactants and products is called delta H, or enthalpy change in a reaction, or heat transfer at constant pressure during a reaction. We'll talk more about it in future slides. Sign conventions in thermochem are all given with regards to the system. If a system absorbs heat, it's positive. If a system gives away heat, it's negative. There is a concept of state functions. State functions depend upon initial and final states and are not dependent upon the path taken. For example, if this is a hill and somebody goes straight up to the hill versus a spiral path, altitude or the height is a state function because it's independent of the path taken. But the work done by the car or the traveler is not the same in both cases, because in one they had to take a longer path versus a shorter path. Here is a picture showing state function as boiling point. State function as about to reach 25 degrees Celsius water. So temperature as state function. Whether you cool off a boiling water at 100 degrees Celsius or you heat up the ice at 0 degrees Celsius to get water at 25 degrees Celsius, the path doesn't matter. The temperature is independent of the path taken, and that's a state function. So you've written many equations so far, chemical equations with reactants and products. Now we write a thermochemical equation. In a thermochemical equation, in addition to reactants and products, we also include an energy quantity, which tells you during a reaction how much heat is absorbed or released. When you see delta H negative, you know it's an exothermic reaction, meaning heat is produced on the product side. And if delta H is positive, then heat is on the reactant side, or heat is absorbed during the reaction. If you reverse a reaction, then value of delta H is reversed, meaning if I were to write the equation 2HCl gives me H2 plus Cl2, the value of delta H will become plus 185 kilojoules. If I were to double this reaction and write 2H2 plus 2Cl2 gives me 4HCl, then delta H will be 2 times negative 185 kilojoules. So this is a table showing heat of formation of Al2O3, or heat of reaction, not heat of formation, I take it back. Heat of reaction for formation of 2 moles of Al2O3 from 4Al and 3O2, and delta H for this reaction is negative 3351 kilojoules. How you write the reaction is you write the reaction and then you can write heat on the product side or heat on the reactant side for an endothermic reaction. It will be totally fine to write, instead of heat as plus heat, you can write delta H as negative 3351 kilojoules, and you can write delta H as positive 182.6 kilojoules here instead of writing this and this. Both mean one and the same things. So few more facts about enthalpy. Enthalpy is the heat content of the system at constant pressure. However, it is hard to measure enthalpy, so generally we measure changes in enthalpy. So changes in enthalpy is the heat released or gained during a reaction at constant pressure. Enthalpy change is an extensive property, meaning if you double an equation, then enthalpy change doubles. If you halve an equation, enthalpy change halves, and so on. It is not possible to measure the heat content of the system, as I just told you. That's why we generally talk about enthalpy change. The units of enthalpy change is kilojoules per mole, and this per mole, guys, is per mole of reaction, which means when you take 1 mole of hydrogen, mix it with 1 mole of chlorine, and make 2 moles of HCl, then so much heat is released. So it is not per mole of hydrogen or chlorine or HCl, but in a 1:1:2 ratio of these, that is called heat of reaction. So heat of reaction is basically different between the energies of products and reactants. And if products are at higher energy, then it's an endothermic reaction, delta H is positive. And if products have lower energy than the reactants, then delta H is negative. Some more additional information about enthalpy. It's a repetition. If you double a reaction, enthalpy doubles. If you reverse a reaction, enthalpy changes sign. And enthalpy, this is a very important point, depends upon the state, or like if it is solid, liquid, or gas of a substance. Water as liquid and water as gas will have different delta H reaction. Now, enthalpy of formation is defined as amount of heat released, generally it is released, or slightly absorbed when 1 mole of a compound is formed from its constituent elements. So there are 2 conditions. 1 mole of a compound should be formed, and what should it be formed from? Its constituent elements. So ammonium nitrate is formed from nitrogen, hydrogen, and oxygen, and you have nitrogen, hydrogen, and oxygen in this equation, so that's fine, but you're not forming 1 mole of compound. So this is delta H reaction, which is 2 times heat of formation, because you're making 2 moles of compound rather than 1 mole. Now, sometimes we put this not sign on heat of reaction or heat of formation. This not sign tells you that you're talking about formation of 1 mole of compound under standard state, meaning at 298 kelvins or 25 degrees Celsius. This is another heat of formation equation for ethanol. Ethanol is formed from carbon, hydrogen, and oxygen. And if you have any element in its natural state, then its heat of formation will be 0. What I mean by natural state is carbon occurs as solid. So carbon as solid will have a 0 heat of formation. But if you look at heat of formation of carbon as gas, you will see a value because carbon does not exist as gas in nature. Now here I just wanted to bring your attention to something. Let's say I write a reaction where H2O2 breaks to form H2O and half O2. Will we call heat of reaction of this reaction as heat of formation of water? No, we won't, because water is not being formed from its constituent elements. So what will be the equation for heat of formation of water? Hydrogen plus half oxygen gives you H2O. Now in this case, heat of reaction will be heat of formation. Another little point, if you look at the heat of formation table, the larger the negative value of heat of formation, the more stable the compound is. So here you see this one seems like a pretty stable compound, glucose. You don't see it decomposing, nothing, it just stays there. Pure elements will have a heat of formation of 0 and close to 0. And you'll have some positive heat of formations too. Positive heat of formation means that the compound took some energy to form. It's not very spontaneous. Now, heat of combustion is when 1 mole of compound is burned, completely combusted in air. And you know that hydrocarbons burn to form carbon dioxide and water. So heat of combustion of carbon is the same as heat of formation of carbon dioxide. Because when 1 mole of carbon dioxide is formed from its constituent element is the same equation as when 1 mole of carbon is burned to form carbon dioxide. So heat of combustion of carbon is same as heat of formation of carbon dioxide. So if you had to write a thermochemical equation for this, I suggest you pause it, write it, and check your answer. It will be C6H6 plus O2. You know it forms CO2 and H2O, and delta H will be negative 3169. That's pretty high, kilojoules per mole, but we need to balance it 6 and 3. So this is the balanced thermochemical equation for heat of combustion of benzene. Now, enthalpy or heat of fusion. So we use the terms enthalpy or heat interchangeably because most of our reactions happen at constant pressure. So enthalpy of fusion, fusion in chemistry means melting. Enthalpy of fusion is amount of heat required to melt 1 mole of a substance at its freezing point. And heat of fusion for water is 602 kilojoules per mole. Remember, to melt ice, heat of fusion for, it should be ice, not water, is 6.02 kilojoules per mole. And to melt ice, it's an endothermic process. Heat is taken in, hence it is positive. So in phase change from ice or solid to liquid to gas, going this way is endothermic and going that way is exothermic. And let's continue on with thermochem. So enthalpy of reaction, remember we talked about delta H reaction is for 1 mole of reaction. And if you double it, you double heat of reaction. Also guys, remember in a balanced chemical equation, it is for moles. If you have to figure out for grams, you got to convert the grams to moles. Can you pause, take a second and do this problem and come back? So you know that 16 grams or 1 mole of CH4 produces I'm sorry, 100 grams of CH4 will make how much heat? when 16 grams of CH4 produces negative 890 kilojoules. And then I don't have a calculator on me, but you can do this calculation and figure out the answer. Now, if you reverse a reaction, remember, you change the sign of delta H. It's a little repetition, but it's an important concept, so it's good to see, good to get a second look at it. Hess's law says whether a reaction is carried out in one step or multiple steps. Delta H is independent of the path taken, meaning if you conduct a reaction in 3 small parts. So let's say A reactant has to form C product, but you go instant A to B to C. Then the sum of heat changes, delta H1 between A and B and delta H2 between B and C will be equal to overall A to C. So whether a reaction conducts in one step or multiple steps, delta H is the same. And Hess's law is used to figure out heat of reaction for those reactions that are hard to conduct in the laboratory. Either they make too much heat or go very fast or are injurious to health. So in such cases, you can figure out 2 or 3 reactions when combined together will give you the overall reaction, and you can conduct these to calculate overall heat of reaction. So your idea with Hess's law is to calculate overall heat of reaction for a desired reaction. In this example, the desired reaction is this, and you have to use or manipulate these 3 equations to get this. So look at what you need from the first equation. You need C3H8, but that's on the reactant side, so you'll need to reverse it. From the second equation, you need, so this is the inverse reaction in blue. And then from this equation, you need carbon dioxide, but that's on the product side, so you keep it like that. But you need 3 carbon dioxide, and you only have 1 here, so you multiply it by 3. Remember, when you multiply it by 3, delta H gets multiplied by 3 too. This 3 is actually multiply this whole thing. And then the third equation, you need water, but you need 4 of those, so you multiply the whole thing by 4. And then when you add them, this O2 and O2 make 5O2, and hydrogen and this is H2, and hydrogen cancels out and carbon cancels out, and you have leftover C3H8, oxygen, CO2, and H2O. So that was one way Hess's law is being used. Another way Hess's law can be used is if you know heats of formation of different reactants and products, then you can use this equation. Heat of reaction is if you sum up all the heats of formation of products and subtract heat of formation of reactants from that, then you get heat of reaction. So in this reaction, if you had to calculate heat of reaction, you'll take 3 times heat of formation of CO2 plus 4 times heat of formation of liquid water. Keep an eye on the state, guys. Heat of formation varies with the state, so you'll go for liquid water, non-gaseous water, minus heat of formation of C3H8 plus 0, because pure elements have 0 heat of formation. The next concept here is calorimetry. Calorimetry is a methodology to measure the amount of heat transferred or enthalpy change for a reaction. And you need to know a few terms. Heat capacity is defined as amount of heat required to raise temperature of a substance by 1 Kelvin, while specific heat has a mass unit to it, so Q is mc delta T, where this is specific heat is the amount of heat required to raise temperature of 1 gram of water by 1 degree Celsius, or 1 gram of substance by 1 degree Celsius. So the difference between heat capacity and specific heat is specific heat has a mass unit to it. So conceptually, specific heat or heat capacity tell you how quickly will something heat up. So a metal has a very low heat capacity, while water has a very high heat capacity. And you use this formula MCAT, Q is mc delta T, multiple times. Be careful about the units though. Calorimetry, there are two types of calorimeters, constant pressure or coffee cup calorimeter and I'm sorry, and constant volume, which is bomb calorimeter. I'm not going to go over bomb calorimeter, it's not in the syllabus, but coffee cup calorimeter we'll spend some time on. Coffee cup calorimeter gains its name for the way it is set up. It's really a coffee cup. This is a picture of bomb calorimeter, so I'm going to skip through it. In coffee cup calorimeter, the basic assumption is Q of reaction plus Q of calorimeter is 0. And Q of reaction is equal to minus Q of calorimeter, which is equal to M mass of solution, specific heat of solution, and temperature change of solution, which are rather easy to measure in a laboratory situation, and then you get Q of reaction. And generally we take Q of solution to be same as water. There is not much difference. Note the values of specific heat are derived units, so they are joules per gram degrees Celsius. So delta T in degrees Celsius or Kelvin is the same, but the absolute value will be different. So this is a picture of constant pressure or coffee cup calorimeter. You have double, for insulation, you have two coffee cups, and then you put the solution or the reaction in there, and then you have a thermometer to measure temperature change, and you put an insulating material on top to reduce the heat transfer to the environment. And the formula you use is MC delta T. Now, how does heat transfer work during phase changes? And this is a great heating and cooling curve animation, and I'll take you there. So in this animation, this is called a heating cooling curve. This shows what happens as you add heat to ice. So you start with ice at negative 40 degrees Celsius. If you give it heat, its temperature steadily rises till it hits 0 degrees Celsius. At 0 degrees Celsius, there is equilibrium between ice, and at this time, it is all water. And during that time, the temperature doesn't change because all the heat is being used to overcome intermolecular forces of attraction, which is potential energy. Remember, it's only kinetic energy that changes the temperature. Then when you keep heating this water at 0 degrees, its temperature rises till 100 degrees Celsius, and then between 100 degrees Celsius water and 100 degrees Celsius steam, temperature stops rising for the same reason. If you notice, guys, heat of vaporization is so much higher than heat of fusion, because in heat of vaporization, you are overcoming most intermolecular forces. Remember, between gas particles, there are not many intermolecular forces, but between liquid particles, there are still some. So you're not breaking all intermolecular bond in transition from here to here, but here to here, you are breaking all of them. And if you continue heating 100 degrees Celsius steam, its temperature will rise and it'll get more than 100 degrees Celsius steam. So how do you calculate heat transfer at every phase? In the non-flat portions, or during when you're not changing a phase, like here and here and here, you use the formula Q is MC delta T, where M is the mass, C is specific heat. Please note specific heat changes with the phase. So solid ice has a different specific heat. Liquid water, which all of us remember, is 4.184. And steam will have a different specific heat. Hopefully these quantities will be given to you and you don't need to memorize them. On the flat portions, you can't use this formula because delta T is 0. How you calculate heat in the flat portion is you take the mass and multiply delta H with it. Or you take the moles and multiply delta H with it, because you know to vaporize 1 mole of a substance, you need that much heat. So you can use that for calculating heat transfer during the flat portions. Now I'll go back to the PowerPoint. So that was about calculating energy at phase changes and in the other non-flat portions. Now the last part of this podcast, and it's been a long podcast, is talking about spontaneity of a chemical reaction. Some reactions occur on their own, some don't. So why do some reactions occur on their own? Well, there are two factors that are acting. One we just studied, which is called enthalpy change. And for a spontaneous reaction, generally the exothermic reactions are spontaneous and endothermic reactions need heat or are not spontaneous. But there is another factor that works towards spontaneity, that's called entropy. In the simplest terms, entropy reflects the disorder of a system. So between solid, liquid, and gas, gas has highest entropy followed by liquid followed by solid. And increase in disorder or a positive value of entropy change is spontaneous, while negative value is non-spontaneous. So the two factors determining the spontaneity of a reaction are delta H and delta S. And how they work with each other, what's the net of them, determines the spontaneity of a reaction, which is called delta G or Gibbs free energy. I'll talk about it in a couple of slides. Let's now focus a little bit more on entropy. Entropy's units are kilojoules per mole Kelvin. There's also a temperature unit. Remember, delta H was just kilojoules per mole. And the way you can predict entropy of a substance is look at the states. Gases have the highest, followed by solid. If the states are the same, then look at the number of moles. The higher the number of moles, then greater the entropy. And these number of moles generally are for gaseous moles. But you can look at overall moles as well. Greater the number of moles of reactants or products, higher the entropy. And then look at the volume of a container. If you increase the volume of a container, it will result in increased entropy, because as you increase the volume of a container, what happens now? There is more room. So if you had lesser volume in a container and you had 1, 2, 3, 4 particles, now in larger volume these particles have more room to move around, randomize. If pressure is increased, then the entropy decreases for the same reason as volume. Now let's look at the net effect of these two delta H and delta S factors that impact spontaneity of a reaction, and that's called Gibbs free energy or delta G. This equation is called Gattis equation, or delta G is equal to delta H minus T delta S, where delta G is Gibbs free energy. A negative sign of Gibbs free energy shows spontaneous reaction. Delta H, negative sign of it shows spontaneity, and for delta S, positive sign shows spontaneity. But ultimately there are cases where delta H is positive, but because the entropy is increasing, the reaction still happens. So you have to kind of take the net of these two factors and then predict if a reaction will be spontaneous. We'll be doing that with this slide. So if delta H is negative, which is spontaneous, delta S is positive, both of these factors are spontaneous, then delta G will be negative and the reaction will be spontaneous. Last scenario, where delta H is positive, meaning non-spontaneous, delta S is negative, meaning non-spontaneous, reaction will be non-spontaneous because both the factors are pointing to the same direction. The little trouble arises when both of those are contradicting each other. Then temperature becomes a factor. So if delta H is negative, but delta S is negative, so you know delta G is delta H minus T delta S. So you want to get a negative sign here. Delta H is already negative. You know temperature is always positive, and you have this negative sign. So two positive negative multiplied together will be negative, and then negative negative will be positive. So this entire quantity is positive. If you want overall result to be negative, then this quantity should be small. And to keep this quantity small, this reaction should be occurring at low temperature. Hence, such reactions are only spontaneous at lower temperature when this quantity is smaller. And if you look here, if delta H is positive and delta S is positive, so again let's write the Gattis equation, and delta H is positive, T is always positive, it's absolute temperature, and this is positive. Two positives and a negative, so this is positive and this is a negative. If you want overall value to be negative, then this factor should be larger than this. That's why this is only spontaneous at higher temperatures. And that is the end of Thermochem podcast. Thank you for listening, guys.